All right, hey everyone. Like I said, my name's Vickery. I'm a second semester environmental science and policy master student. My background is actually in ecology. So I studied environmental sciences at Emory University in Atlanta, and then went on from there to work as an ecologist at the Georgia Department of Transportation in Atlanta. So here at USF, let me see if I can get to the next slide. One sec. Yeah, so like I mentioned, for those joining us, we were having some technical issues getting our slides to flip through. So there's going to be times where I have to jump out of the slide to restart things. So just bear with us. So here at USF, my research basically looks at estuaries. So I'm interested in circulation patterns in estuaries, and I'm using numerical models to see how we can improve circulation in estuaries. The specific place that I'm doing my research is called Fort DeSoto Bay, which is just south of St. Pete. It's a very cool place. I highly recommend going if you haven't been there. But the goal of this research is to find ways that we can use improved circulation as sort of a tool or a mechanism for restoring seagrass and mangrove communities. So if there's one thing I want everyone to kind of take away from this lecture today, it's really the importance of tidal circulation. So it's important to remember that estuaries are tidally influenced areas. So all of the ecological and biological processes that happen within estuaries are really dependent on that sort of rhythmic ebbing and flooding of the tides every 6 hours. So as far as water quality is concerned, the temperature of the water, the clarity, the dissolved oxygen, the nutrient balance, all of these water quality parameters are regulated by that tidal flushing. So when humans come in and we make alterations to the environment that inhibit that circulation flow, we generally will see reductions in water quality. And the same thing goes for ecological processes as well. There's a number of processes that are closely linked with circulation patterns. So for example, the phytoplankton that live in estuaries, they have a very limited swimming capacity, so they actually rely on those circulation patterns to transport them and help to disperse their genetic material throughout the environment. Another process that's dependent on tidal circulation is something called outwelling. So a large percentage of the organic material that's actually produced in the estuary, which we collectively refer to as detritus, this detritus is actually exported from the estuary environment to marine ecosystems where it will actually subsidize those ecosystems. So this is a very important process, and it's one that is entirely dependent on that circulation. And then finally, some physical processes as well. So depositional processes are very important in estuaries. You have all of this sediment coming in through the rivers, and it's being reworked in the estuaries, and that helps to maintain salt marshes. It helps to maintain mangrove communities, barrier islands, and that whole process is driven by circulation. So for all of these reasons, circulation is really seen as a critical component to restoring estuaries, and any restoration efforts that don't specifically address circulation are likely to be ineffective. I think we might have some people waiting to get in, so let me just check to see really quick. Oh, no, we're good. Okay, so before I show you guys my research, I wanted to introduce a discussion question, and you don't have to answer this now, but start thinking about this, and as I go through the rest of my presentation, if an answer pops into your mind, just go ahead and use the chat box, and then once I get to the end, we'll review all the answers. So the question is, what factors, and those factors could be man-made factors or natural influences, but what factors influence circulation in estuaries? Got it? Cool. All right. Okay, so I'm going to start with kind of a zoomed out view here of Tampa Bay so everyone can get a sense of where we are geographically. So St. Pete here in the middle, Tampa over here on the right, and then the Gulf of Mexico here. So the place I'm actually doing my research is way down here at Fort DeSoto Bay. Let's zoom in on that. So like many estuaries here in Florida, this area has a very extensive history of human alterations, and these alterations have had a really negative effect on circulation patterns here. So if you start to look closely, you can see this kind of lattice work of these dredge channels that have been cut through the estuary, through the seagrasses, this one coming down here, these over here. So the seagrasses themselves actually exert sort of a frictional force on the flow field. And, excuse me, and the dredge channels being a little bit deeper and sort of lacking that vegetation, they exert less friction. So one of our goals was to use our model to kind of tease this out and see how these two factors work together to influence circulation in the estuary. And then another thing that's influencing circulation, probably the most obvious feature, is this large causeway, which cuts straight across the estuary. Excuse me. So this causeway, along with the smaller one here, they were built back in the early 1960s, I believe, and basically the sole purpose was just to provide vehicle access to the island. Unfortunately, they had a very negative side effect, which is that they completely obstructed that circulation between the western side of the estuary and the eastern side. And as a result, if you remember what I talked about on my last slide, when you inhibit circulation, you get water quality problems. That's exactly what happened. So down here, where circulation had essentially shut down, dissolved oxygen levels plummeted, temperature went really high, and all of the seagrass ended up dying off. So the county, kind of recognizing that this was a major issue, decided to install a pair of bridges, which you can actually see here. So this one here on the main causeway, which you've probably driven over if you've ever gone to Fort DeSoto, and then the smaller one here. So these bridges basically breached the causeway and allowed that circulation regime to restore itself. The ultimate goal here was to help restore those seagrasses. So that's basically what my research is looking at, how these bridges are influencing circulation across the entire estuary. Let's see if I can pop back over to my slides. So this is just kind of a ground view of the bridges that I mentioned earlier. So this is the one up here in the top right that you've probably driven over if you've ever been to Fort DeSoto. And then on the bottom left is the maintenance road. So you can see there's a pretty substantial volume of water that actually goes through these bridges. And our goal was to actually use our model to see exactly how much of that water is going through. So to run the model, we actually need 3 different data sets. The first is tide level data, which is represented here by these little symbols, these little round symbols. That's where we installed our tide level gauges. The second is the current velocity, and those symbols are marked here at the bridges with the little triangles. And the third data set is something called bathymetry, which I'll show you on the next slide. So on the left, we have our raw bathymetry, and this is basically just the elevation of the seafloor. That's what bathymetry means, essentially. So we got in a boat and we actually rode these lines right here and collected that elevation data. And then we plugged it into our model over here on the right, and the model is very clever, and it can extrapolate between those points and generate something called a digital elevation model, which is what you see here. So the warmer colors represent shallower areas, the cooler colors represent somewhat deeper areas in the estuary. And these are just some photos showing us installing some of that equipment. So top right and bottom left is where we were installing our velocity gauges. And then top left is me collecting some bathymetry data. So that pole I'm holding there there's something mounted on the end of it called an RTK, which tells us basically the elevation when you stick it up on the ground. So that's how we collected our bathymetry data. And then bottom right, you can see us installing one of our tide level gauges. So, excuse me. So once we have all of that data, we execute the model, and that's what you can see here. So this is kind of your quintessential modeling photo, where you can see all of the flow arrows coming through, showing the direction of the water. And it's important to remember that velocity, that's basically what our model is giving us, is velocity. And since velocity is a vector quantity, it has a magnitude and it has a direction. And the magnitude here is represented by colors, and the direction is represented, simply by the direction of the arrows. So looking at this, you can see where the water is flowing, and you can see how fast it's flowing, which is a pretty cool tool to have. And what really makes this model so powerful is that we're actually able to manipulate the environmental conditions here. So, for example, if we wanted to see what would happen if we closed off one of these bridges while leaving the other one open, we can do that. If we wanted to see what would happen, for example, if another bridge was built right here, we could also do that. Or if one of these dredge channels was filled in with seagrasses, the possibilities are really endless, and that's what makes the modeling system so awesome. Okay. So I wanted to very quickly show you a poster that I put together to kind of summarize all this data. Like I mentioned earlier, our goal here was to see how much those 2 bridges are influencing circulation. So this is kind of where I compiled all of our results over here on the right. So we did something called tidal prism analysis, which sounds complicated, but in reality, all we're doing is comparing the volume of water that flows through those 2 bridge openings to the entire volume of water that flows into the estuary. And that gives us a percentage. And you can see here highlighted in yellow, 25% of the water that flows into the estuary during the flood tide is actually going through those bridges. So that's a pretty significant figure. And it kind of shows us that these bridges play a very, very important role in circulation within the estuary, and it kind of helps to validate the entire infrastructure project. So we were pretty happy with those results. Let's see. Okay, so from here, we have some plans to use historical imagery to kind of reconstruct what the circulation patterns were like back in the 1940s, predating the installation of those causeways, predating all those dredge channels, basically predating all of the human influence that Fort DeSoto has. So if you look at this image here, you can see that there's no causeway, there's no dredge channels. This is basically the natural state of Fort DeSoto. So we're going to try and use our model to basically wind back the clock and recreate that circulation regime. All right, so coming back to our original question, let's see who has put anything in the chat box here. Okay, so far, no responses here. If anyone wants to hazard a guess as to what factors, yes, tide, great. Dredge channels, fantastic. Perfect answers. So, yeah, runoff as well. I'll wait a few seconds to see if there's any more coming in. Okay, those are all fantastic answers. So let's see if I can get to the next slide. Okay. So we can essentially break down the factors that influence circulation into two categories. You have your frictional forces and buoyancy forces. So frictional forces mainly would be your submerged aquatic vegetation. So your seagrasses, your marsh grasses, the mangrove roots, they all exert friction on the flow field, and that inhibits circulation within the entire bay. Oyster reefs also play a role, dredge channels, like Audrey mentioned here, and then propeller scars as well. So there's lots of boats that come in and out, and they kind of scar up the floor of the estuary, which is no good. We don't like that at all. And then buoyancy forces as well. I mean, you have to remember that circulation happens laterally, but it also happens vertically. So that vertical mixing is driven by differences in density, which basically have to do with the salinity of the water and the temperature of the water. And then a couple other factors as well. So the man-made structures, the geomorphology, which is just the shape of the estuary itself, the bathymetry, the wind, and then the tide, which someone mentioned, and the Coriolis effect also plays a small role. So with that, I'm actually going to hand it over to Francesca and let her tell you guys a little bit about some beach processes.
Thanks, Gray. That's really cool stuff. Okay, I'm gonna share my screen. There we are. Okay, so I am focusing my thesis a bit more on beach processes, and I'm in the earlier stages of planning my project. So I'm mostly gonna be talking a bit about beach processes in general, and then talk a little bit about what my thesis is gonna be about. So, sediment, sand, or as we also call it, sediment, is constantly moving onto and off from the beach. There are two main types of sediment transports. There's longshore transport, which occurs during regular climate conditions, and there's also cross-shore transport, which occurs during storm conditions. But what I want you guys to take from this is that sand is constantly moving in the beach. The beach is constantly changing shape, and it's normal for beaches to grow or become smaller. And this has to do also with the sedimentary budget of a beach. And that is the amount of sand that it needs to stay constant, basically. Oops. And so if we have more sand coming onto the beach than coming off from it, we have erosion in the beach, meaning the beach is becoming smaller, as we can see in this picture from the coast of Puerto Rico. This was after Hurricane Maria, and a lot of beaches got eroded away after the hurricane. And when we have erosion, this is usually due to having a negative sedimentary budget because of, more sand leaving than coming onto the beach. And when we have more sand being deposited on the beach then is leaving, then we call this accretion, and this is due to having a positive sedimentary budget, as we can see in the picture here on the right. So erosion has been a big problem in the last few decades. Erosion rates have been going up in beaches all over the world. And this is due to a few factors. What takes sand away from the beach is waves and tides. You know, these are normal processes, but then this can also be exacerbated by human activity and global warming causing sea level rise, and also increasing amount of hurricanes and more intense hurricanes. So as we know, sea levels have been rising in the past few decades, and we expect them to continue rising. So, you know, we have been looking for ways to protect beaches and preserve them. These pictures here are more pictures of Puerto Rico right after Hurricane Maria. Like, that hurricane just took away entire beaches. It was crazy. And here are some examples of what coastal scientists and engineers do to deal with this beach erosion. So there are two main approaches to preserving beaches. One is what we call a soft approach, and then there's also hard engineering structures. In the last 40 years, Florida has been using soft approaches such as beach nourishment, and we haven't been using hard engineering structures. Before the beach nourishment was taking place, we did have groins such as these. This is an example of the engineering structures. You can see it in the picture furthest left. This is Miami Beach. Before nourishment and after. Nourishment just means that sand is being dredged up from offshore and being placed on the beach. So they're basically making a new beach. And hard engineering structures are seen as kind of outdated now. You know, there are advantages and disadvantages to both of these approaches, but the truth is that the engineering structures, and we can see more of them in the pictures to the right. These are, the top picture is seawalls, and then the bottom is more groins. These are in the coast of Cartagena in Colombia. And the thing about these structures is that they don't really end up preventing that much erosion. The erosion keeps happening, and it usually becomes worse in other areas due to these structures blocking sand from reaching other areas it needs to reach, and causing then, you know, interfering with the sedimentary budget. And that is why I'm interested in studying beach rocks in Puerto Rico. So that's why I kept mentioning Puerto Rico earlier and showing pictures. The beaches of Puerto Rico have been eroding for a while now, and a bunch of them just disappeared after Hurricane Maria. Oh, something also I didn't mention earlier about the human factor with the anthropogenic effect on beaches. You know, with all the building on the coasts, that also affects beaches. Like, with all the buildings, sand might not reach as easily. So because of all these factors and sea level rise and the hurricanes, beaches have been eroding in Puerto Rico. And what this has caused is for beach rock to be unearthed. Beach rock that was lying underneath the sand in the beaches just became exposed. And we're interested in seeing what the effect of having this beach rock exposed will be to the rest of the sands, will this act just like a hard engineering structure? Will it keep the sand in place a bit more, or will it cause to erode more easily? And these are important questions because by studying this, we might be able to find new and more eco-friendly ways to protect beaches in the future. Are there any questions for me or for Gray? Thank you.
Okay, I think I can turn my video back on now since I don't have to do any more slides, so it won't freeze up.
And we're also, you know, open to answering questions about our experience as students or as geology or environmental science students. I don't know if you guys are interested in studying these things in college or want to know more about getting into grad school or whatever. I'll answer
Major?
first. Yeah. Oh, okay.
You can go ahead, Francesca.
Yeah. So I studied geology as an undergrad, and I'm still doing geology as a master's student. What's your major grade?
And I'm environmental science. So I studied environmental sciences as an undergrad, but I kind of had a concentration on ecology and geology. And now as a grad student, I'm also studying environmental science, but my focus now is more on coastal processes. I'm also actually dually enrolled, I guess you could call it, in the business school as well. So I'm taking some business school classes too.
And I'm a professor in the environmental engineering program, which is part of the Department of Civil and Environmental Engineering. So, and my undergraduate degree is in environmental engineering. There was a question about going back to the poster.
Sure. Let me do that really quick. I can actually full screen this. Give me one sec. I guess it's not going to work. Yeah, so this is the poster that I gave at a conference back in February down in Sarasota. The conference is called FSBPA, which is the Florida Shore and Beach Preservation Association. And it's basically just a consortium of consultants and government agencies whose basic directive or objective is to find ways that we can preserve the longevity of our coastlines. With sea level rise, you know, preserving the coastlines is a big important factor that people are trying to, a big question that people are trying to answer, basically. So poster I presented alongside with a couple other students down there. Let's see, I got a question in the chat box. And essentially, we're just showing the data collection process, some of the statistical analysis we did that you can see in the middle here. It looks complicated, but it really isn't. All this is a comparison of our modeled values with our measured values, because at the end of the day, that's what a model does. It makes predictions. So if you have the actual data to compare it to, you can know whether or not your predictions are accurate, which is what this graph shows here. So yeah, that's pretty much the poster. Data collection. It didn't take too long because the data, the instruments that we use, we actually leave them out there. So all we have to do is place them and they do their thing. We come back a couple of weeks later, we pick them up, and then we download the data. So we left them out there for an entire, what's called a spring neap cycle. There's a lunar cycle called a spring neap cycle, and that's the entire length of time that we tried to capture, which ended up being a little bit over 4 weeks. So I have another question here. How did I know that I wanted to get into environmental sciences? This is something I realized when I was an undergrad taking my very first geology course, actually it was. And it was kind of just an aha moment. I immediately knew that's what I wanted to do. And at that point, I'd actually been kind of flip-flopping between majors. I was pre-pharmacy at one point, if you can believe it. And then I thought about being a linguistics major. I thought about being a business school major, and then ended up landing on environmental sciences after taking that geology course.
You have another question.
Oh, sorry. Unexpected difficulties. So barnacles. Barnacles are a major issue. Whenever you're doing field work that involves instruments that go in the water, you have to worry about barnacles. They are just very, very insidious. They get all over your equipment. You have to go every couple weeks, scrape them off with.
One of the unexpected difficulties we're having now is the COVID pandemic. So I think the students I have in my lab who are, had started research already are fine because they're able to keep their experiments going. But any new students have to learn how to do different methods of analysis and set up different equipment in the lab. And so it becomes really hard to start something new if you can't have people close to each other. One of the things that people is kind of maybe a misunderstanding about science is that people think about scientists and they think about them working kind of in solitary, but really science and working in a laboratory or doing field work is a very collaborative experience, and you're always working with teams of students and researchers all together. And so it's something that's really hard to do if you can't be close to people.
Yeah, and that's something that's affecting me as well, because I was supposed to be going to Puerto Rico around now, but I'm not able to because of COVID.
Yeah. So I wanted to follow up really quickly on Elisa's question about environmental science as a major. I want to emphasize that to everyone that environmental science is a really, really great field to be in right now. I would actually argue, excuse me, I'd actually argue it's probably one of the most marketable degrees that you can have right now. And the reason for that is because it encompasses so many different fields. So of course you have geosciences, but there's also economics and social sciences and natural resource management, all of these fields that kind of fold into the umbrella of environmental science. So every time I go online and do a job search with just environmental as a keyword, I'm blown away by how many companies are hiring environmental scientists right now. It's really awesome. So if anyone's interested in joining that field, I highly recommend it.
And I'm answering the question of if I can change my location. I guess I could, but I'm not doing that yet. If it keeps being a problem long enough, then I'll have to, I guess. But for now, I'm just gonna start writing my thesis, just the background part. So I'm just reading a lot of scientific literature and trying to learn as much as possible, and then I'll be better informed once I finally get to do field work. So it's not really time lost.
It's going to be interesting to see the effect of this on research. It may be that we find out that students are more productive if they have a little bit more time to think. I have one colleague, his name is Dr. Cunningham, and he always makes the same joke, and he says, let me see if I can I can't remember how he says it, but he says something like, 3 weeks in the lab will save you 1 day in the library. I think that's what he, in other words, he'd like students to spend a little bit more time in the library thinking about their research and seeing what other people have done first, and then go into the lab and then do the research. I actually have a little bit of a different philosophy. I like students to spend time in the library, but I also feel like sometimes if they spend too much time in the library, they start getting afraid to start something in the lab. They're afraid to handle the chemicals, and they're afraid to just try something. And so I think you need to have a balance. Some people, you know, some work in the library, but also kind of don't be afraid to just jump into things in the lab. So you have a question about how long does the whole process take?
So for me personally, it only took 8 months. I actually know the exact amount of time it took because I presented that poster in February and I started in August. So it was pretty quick, actually. We were out there as soon as I came to USF. We were out in the field the first week I got here, and we were putting that field equipment out. And then within a couple months, we'd done our preliminary data analysis and then gotten our conclusions around December, and then I was presenting that poster in February. So I think it just depends on how ambitious you are and how much time you have on your hands. My course load during the first semester was pretty light, so I was able to focus pretty heavily on the research. It did take some long days and some long nights in the lab, running that model, crunching those numbers, and that model takes a long time to run too. We actually have 6 different desktops running the model simultaneously because you have to wait an entire weekend for it to finish executing. So if you want to be able to run different simulations, you have to have different computers. So we have a whole cluster of computers that we use. But the process is a lot of fun, and it really just it depends entirely on how ambitious you are and how fast you want it to happen, really.
So my students do research on biological treatment processes, like how to improve wastewater treatment. And for those experiments, they tend to take a little bit extra time because you're working with microorganisms. And so sometimes we have to build new types of bioreactors. We have to test them out. We have to seed them with microorganisms. We have to run them with wastewater and collect data and analyze the data. And sometimes you do something wrong and you come into the lab and you found that your experiment died. I once had an experience when I was in graduate school where I had a pump that was supposed to pump some benzene, toluene, and xylene into a bioreactor. And the microbes were doing a great job of biodegrading these toxic chemicals. And then I accidentally set the pump at the wrong speed, and I put tons of benzene, toluene, and xylene in the reactor, 10 times as much as I had wanted, and I killed my experiment. I had to start over again. So unfortunately, things like that happen. But those are learning experiences too. Sometimes we have something like that happens, and then we see how long it takes for the system to recover, because those kinds of things happen in the real world also. Some chemical company can clean out a tank of reagents, and all of a sudden a bunch of toxic chemicals go into the bioreactor, and then the operators and engineers have to figure out how to get it back working again. So those kinds of things, sometimes even though you're crying at the time and really upset that you messed up your experiment, you can learn from those things too, like the barnacles.
Those experiments sound really cool, honestly. And yeah, I still don't know how long mine's gonna take, but I think it sounds like just 2 visits to Puerto Rico would be enough. So I'm assuming that mine will end up taking more or less around the same as Gray's stuff to run, because I also have a similar process of collecting data and then running models. So hopefully I'll be able to do that soon.
Thank you so much for all the information. I'm Mrs. Kulkarni. I'm teacher at Middleton High School, and I have few students here from my class. And they have been attending all the webinars from last few weeks. So everyone selects which one they want to attend. So thank you so much for all the information.
Great. Are you teaching the biotechnology class? Is that because we've had a lot of students from that class?
Yeah, I'm teaching that bio.
When things open up again, maybe sometime your students could come and see our bioreactors in my lab.
That would be great. Yeah, I will keep in touch with you. So now we are almost end of the school year for this year. Right. But the next year, yeah, of course, I hope we get back to our classrooms and all our labs, right? So if we get back, yeah, sure, that could be amazing for the kids to go. And they do a lot of experiments in class, but to go and see the actual lab and things like that would be good. Mm-hmm. Thank you so much again.
You're welcome.
Bye.
Thank you for attending. Bye.
Bye-bye.
Bye.